Good afternoon, eights. Based on what I saw this morning, there were not very many students who submitted work, but the students that did, it seems like they have a decent handle on what is the Pythagorean theorem, like what does it actually say, what is the pattern involved, and how it could be proven, at least using a visual proof. So the things I want to share with you today, this afternoon, are about the Pythagorean theorem, like the history of it, and the Greek schools. And I'm going to try to go pretty quickly because I also have an applied problem set I want you guys to work on, and we'll do some examples in this as well. So the Pythagorean theorem has been useful over human history, but what's really interesting is the history of both the time period and the theorem. Over different time periods, the culture of mathematics has changed massively, and you will see some of that in this presentation. Some definitions of things we'll talk about. The difference between a theorem and an axiom. A theorem is a statement that is proven to be true based on a set of accepted axioms. So we accept these axioms to be true, and we use them to prove theorems. An axiom is a statement that is agreed to be true despite the lack of a proof. So we don't prove axioms. We just assume that they are true, we agree they're true, and we use them to prove other things. Here's some examples. An example of an axiom would be, given any 2 points, there's a point between them. So if I go ahead and draw 2 points here, I think we would all agree that there is not only 1 point between them. If I change color, not only is there 1 point between them, but there are lots and lots of points, like an infinite number of points between these. We don't prove that these points exist, we just make it an axiom. We just accept the fact that there are points there, and we agree to just know that that's true, even though it's unproven, which is dangerous. So a theorem, on the other hand, says things like all odd numbers are of the form 2k plus 1, where k is an integer. So that's just saying if like all odd numbers will be, if I take some integer and plug into here, I would do 2 times something plus 1, and that would get me an odd number, no matter what, all the time. So that's a theorem. It's something we can prove that this is true. This one we just accept that it's true, so it's an axiom. Next ideas. I'm going to try to go quickly through. So Pythagoras was a guy. He lived about 400 years BCE in the Greek Empire, I guess, but at the time they were city-states. So the Greeks would not have considered this an empire by any stretch. It was just a culture that was spreading, the culture of democracy in most cases. He was born in Samos, and if you look at where Samos is on the map, it's in modern-day Turkey, but it's among this big island chain kind of between Greece and Turkey. They had no written numeral system, which is a crazy thing to think about, that we take for granted, the fact that we can write 1, 2, 3, 4, 5. Well, they didn't have that. They used unit distances of rope. So if they wanted to look at relationships between 3, 4, and 5, they would have built things like this out of unit distances on rope, which is crazy to think of the amount of math they were able to do using geometric ideas. And they really had little to no other ways to attack things. So they were very, very geometric in their ideas. Pythagoras began several schools with varying reports of success. He eventually moved to Croton, which was then it was Greece, now it's in Italy, the same way that then this was Italy or Greece, but now it's Turkey in Samos. But Croton and his school blew up. It became a huge school. They competed in the area. And there are lots of legends about him. Some of the legends that you've probably heard attributed to other people were originally about Pythagoras. One of the big ones actually is after Pythagoras moved to Croton, supposedly he walked on water. Like 400 years BC, which is it's interesting. So the Pythagorean school, he was a guy, he started a school, lots of schools actually. His schools were extremely cult-like, and that was normal back in that time. They had rigorous sets of rules. They were all vegetarian. They were not allowed to eat beans. There was a large system of morality and belief, and you had to follow all of these rules or else you could risk losing like anything, your entrance to the school, all the way up to you could be killed for certain things, although those stories are kind of more of legend also. All of the knowledge was contained within the school. Schools in this time period did not give away knowledge. They hid the knowledge, so they were the only ones able to solve these problems. And all new knowledge only carried the name of the school, which is Pythagoras, happens to also be the name of the guy. So all of the knowledge in the school was that one guy, and that's it. An example story I have for you, I don't want to go too much into. Supposedly there's one of the Pythagoreans proved that irrational numbers exist. So the Pythagoreans, with their idea of, for example, that 3, 4, 5 triangle was built into this idea so deeply, they believed all numbers could be expressed as P over Q, which we know as being the rational numbers. So the Pythagoreans believed every number was rational, like all numbers. Well, there's a guy that proved irrational numbers existed, and the legend is that he was killed, like sent out to sea and drowned. Euclid's Elements is important. It's a book that was written, and the reason it's important is that the Pythagoreans didn't write stuff down. So none of this is written down. It's all contained within the school and hidden away from the world. Well, Euclid, I say that here. Since the Greek schools hid their knowledge from each other, there was no written shared documents. So Euclid was the head librarian at the Library of Alexandria. This is one of the 7 wonders of the ancient world. The Library of Alexandria was huge. I wish it still existed. But he attempted to gather all known mathematical knowledge in the world. And he ended up writing a 13-book series called Elements. Today we know it as Euclid's Elements. It was actually the best selling is strange because there's been various amounts of literacy in the history of the world, but it's been the best-selling book through all of history up until last century when it was finally passed up by the Bible. It's still it sold, I think, the second most copies of any other book in history. That might have been broken by Harry Potter. I think Harry Potter might have sold more books than Euclid's Elements. Anyway, he created a system of axioms and theorems that we use still. So his idea of like accepting some things to be true, using them to prove other things. Well, that was an idea of his that carried through to today. Many of the proofs in the Elements were ancient, but since he wrote them down, now all of them belong to Euclid. And we just say Euclid's Elements is the foundation of all of this. The same happened with the Pythagorean theorem. All knowledge in the school carried Pythagoras' name, whether it was ancient knowledge, created by a student, or actually his. It all carries Pythagoras' name. So is he the only one that created the Pythagorean theorem? Obviously not. Good. The Pythagorean theorem is ancient, is known and proven all around the globe. So like the Chinese proved that the Pythagorean theorem was real. The Babylonians proved it was real. Lots of cultures have done this. It wasn't unique. It states that in any right triangle, so down here we have this right triangle, in any right triangle with legs A and B and hypotenuse C, it will be true that a squared plus b squared equals c squared. So yeah, if we add this square down here to this square here, we get this square up here. And you guys saw some geometric proofs of why that's true. To put into practice, so here's some things you'll be asked to do on your homework or on the next assignment. We know this formula. So if I go down and look at this triangle in number 1, our hypotenuse is here. It has to be C. These other legs, it doesn't matter. I'll make that A and make this B. And so then if I look at finding that C side, I know A squared is 10 squared plus B squared is 24 squared equals C squared, which is X squared, which we don't know. 10 squared is 100 plus 24 squared. I should have had that done. 24, 480. Whatever is a number. In the end, you just have to know that here we do still have a squared going on. So you'll have to square root whatever number you get over here. And then the square root of that number will be equal to that hypotenuse. So the same thing will work over on number 2. The only difference, the reason I put it, is our hypotenuse is now here. So that's 30. Oh, sorry. That's C. The others are A and B. And so I end up with A squared plus B squared equals C squared. And then we have to go on and solve it the same way we were solving over here. Sorry, I should have had those squares so that I could finish it real quick, but I only know the perfect squares up to 20. I should know more of them. So you can stop the video now and go for your homework. You have enough. But one fun, quick little extra connection is that in writing Euclid's Elements, Euclid started out with 4 postulates, and then he started 4 axioms, and he started proving things. And then he gets pages and pages deep, and he has a 5th axiom. So this is Euclid's 5th axiom down here. and it's provably the exact same as the Pythagorean theorem. So these are actually the same statement, they just look very different. So since Euclid obviously wanted to prove this but couldn't, so he made it an axiom way late in his book, it went on that people tried to prove this statement for like almost 2,000 years. And we found out later the problem is that both of them have an implicit assumption. The assumption is a flat surface. So over here we can see the Pythagorean theorem is going to be true in this case, and over here we see the Pythagorean theorem will be false. If you're unsure of that, try to extend these and make squares out of these, and you'll see whatever these squares look like, these three squares have to be the same size. So there's no way that we can add two of them to get the third one. It's not possible, so it's false. The fifth postulate here we see is true when we have point P and that line, and there's only one line here that is parallel to that. But if we come over here, we have a line and we have a point, and now there are sorry, I should have drawn it differently. Well, there are lots and lots of lines. No, sorry, there aren't lots. There are 0 lines that are parallel. Any line I draw coming off of this point will intersect at some place. So yeah, and we see the same thing here. Any lines on a sphere, they have to intersect at some place. So there are no parallel lines on a sphere. What we found is that the assumption of a flat surface made this impossible to prove for almost 2,000 years. But eventually several mathematicians in different places seemed to simultaneously do away with the assumption, and they proved there are many worlds of geometry. So the one I've given here is their spherical geometry, but we also have negatively curved surfaces and lots of other types of things that stem from these ideas. So just to note that things go unsolved for thousands of years based on assumptions that we make. And when we fix those assumptions, there's usually like massive progress that happens. So best of luck, Gates. I'll see you soon. Bye.